Hello everyone. In the last video we completed one small spice simulation and these are the results for it. You have the drain current on the y-axis and you have the voltage, the VDS, drain to source voltage, on your x-axis. Okay, so you see a different plots over here, different kinds of plots over here. To start with, let's look into the plots one by one. Yeah, if you see the plot which is at the bottom, which is overlapping the x-axis, that is at VGS equal to 0 volts, and that because you see zero drain current at that point of time. And the reason is when your VGS is 0, your device is not turned on, so there is no channel, so you see a zero, you see a zero drain current. Okay, on just overlapping that, there is one more curve. Last time we had zoomed into this area and we had seen there is one more curve, and that's at VGS equal to 1 volts, where it says that it has just crossed the threshold voltage. So there is some channel, bare minimum channel available for the drain current flow, and you see small amount of drain current during VGS equal to 0.5 volts. Okay, so this is VGS equal to 1 volts, where it has almost crossed your gate, it has almost crossed the threshold voltage, and you see some amount of drain current flowing. Okay, this is at VGS equal to 1.5 volts, this is at VGS equal to 2 volts, and this is at VGS equal to 2.5 volts. So all the hand calculations, all the equations, and I'll come to the equations, all the equations that we had derived, they're all encapsulated in these curves. You take your VGS one by one and you try to plot the drain current, this is what you will be getting. Okay, so let's try to revisit our equations, and we'll try to map this particular curves with those equations. Let's try to do that, so that will give us a better understanding of what is happening between these curves. Okay, so that when we move to lower nodes, when we move to W by L of let's say L equal to 350 nanometers, we will get a clear picture of what is the difference and what can happen when you go to lower nodes. Okay, but before that, let's try to understand this one. So let's say this is the curve. The reason I have drawn this curve at this point, it's because this area of this curve represents a complete different behavior of a MOSFET, and this area represents a complete different behavior of a MOSFET. And the reason is, in this area, if you see, your drain current is linearly increasing. This is your drain current, this is your voltage. So drain current is a linear function of your drain to source voltage, and we had derived that some time back. And over here, your drain current is no more a linear function, but it's a function of 1 plus lambda VDS. That's your channel length modulation factor. So it's a function of 1 plus lambda VDS in the right side area. So if you see, the same MOSFET has got two different behaviors at two different points, and the point is this one. Okay, before this, the device is in the resistive operation, it's in linear region, and over here it's in saturation region, and we had explained the concepts behind it, why all this happens. So we'll revisit these equations again. So in the linear region, we had this particular equation, ID equal to Kn VGS minus VT VDS minus VDS square by 2. So the concept of linear region was that at lower values of VDS, this term tends to vanish. Okay, and your drain current becomes a linear function of VDS, and that's what exactly is happening in this area. Okay, similarly for saturation region, if we just replaced your VDS, this curve is called VDS equal to VGS minus VT. So when your drain voltage exceeds or is equal to VGS minus VT or exceeds VGS minus VT, the situation completely varies. At that point of time, you replace your VDS by VGS minus VT in this equation, and this is what you get. And it tends to that it's a function, it's a function of your lambda VDS. Okay, so your drain current is a function of lambda VDS, but it's not completely saturated, it's not completely constant, but it's slightly increasing, which is a function of lambda VDS. But it appears to be constant. At this point of time, it appears to be a constant. Okay, so these are two different regions of operations, and this is correctly mapped. So this will become your linear region, this region will become your linear region, and this region will become your saturation region. Okay, the good thing about this is we now completely understand what linear region is, what saturation region is, and there will be a region which lies when VGS equal to or less than VT. That's called your cutoff region. A cutoff region is a place, a region in or an area where your device is being cut off, it's being off. Okay, so that is how we are mapping the drain current equations to the curves with the help of some graphical way. So that's a very interesting way, that's a very best way to learn saturation region and linear region of operation for MOSFET. Next, what we'll do is we will take a completely different scenario, a new situation we'll take over here, and that's when your W is 0.375 microns and L is 0.25 microns. Okay, we were looking into 250 nanometer device. So your length, the technology node, now we are looking will be at 250 nanometers or 0.25 micron. and your width is 0.375 micron. So just before that, if you see this particular curve, what do we expect from this particular curves? We expect whenever your W by L is constant, you expect your drain current to be same at any node. That's what is the expectation. Okay, so for example, in this case, if I reduce my L from 1.2 micron to 250 nanometers, if I reduce my W from 1.8 microns to 375 nanometers, the W by L is constant, so we expect the drain current to be constant. Okay, that's what is the expectation, but that doesn't happen for lower nodes, and I'll explain you why it doesn't happen. Okay, so we'll take a different situation where your W is 0.375 micron, your L is 0.25 micron, and the W by L ratio is being kept as constant because we have set some expectation, and we'll try to see if we are able to achieve that or not. And that will not be the case. I'll tell you in some time. Okay, so with that said, we'll bring up with a new spice deck. The spice deck, everything will remains the same as the previous one. The only difference between this spice deck and the previous one is that your W is 0.375 and your L is 0.25, so that your W by L is maintained constant, and rest all the factors, the resistance, the MOSFET type, the VDD, Vin, the dot op and the dot DC, and the model file, everything remains the same except your W is 0.375 and L is 0.25 microns. Okay, so with that said, we'll do one small spice simulation. Okay, so we have entered into that area, and we'll take this particular file. I'll just copy it, and I will source this as dot. So again, I have saved it as .cir file. Let me minimize this. Okay, so yeah, we have sourced the circuit over here. So now this particular ngSpice, or this particular spice, yeah, spice system or the spice software has the circuit information. Okay, now we'll simulate it using the command run. Okay, same this is the same that we used in the past video. We'll now look into the plots. We'll do a set plot, and we'll observe that there is the new DC transfer characteristics has got the name as DC1. So we'll do DC1. Okay, we'll look into display what all the plots are available to us. So we have these are the node names, which are the voltage. If you try to plot this one, you will get the voltage curves now, but we are looking into current curve, so we'll plot VDD branch. So when we plot hyphen VDD, sorry, minus VDD hash branch, and the reason for the negative I had explained in the last video, where it's because of the difference in the conventional current flow versus the flow of electrons. I'll come to that when we enter into device physics lectures. And when we plot it, this is the curve. Okay, so if you see, there are a few things to observe over here. If we have not observed in the previous curve and this one, there are a few things to observe over here. First of all, if you see the difference over here, that has been reduced. That's the first thing. Okay, second thing, in the previous case, the current value for the device in the saturation region and the current over here in this case are different, and I'll come to the exact values of it one. And the third thing is, if you see the difference between two adjacent curves, they appear to be constant. Okay, but they appear to be different in the difference between this particular curves appear to be different in a case where your W by L is constant but your L is 1.2 microns. So we have just talked about three different situations where this curves varies from the previous curve. What we'll do is, since I'm running a bit late out of time, I have to take this particular curve. We'll just minimize this one. Okay, we'll take this curve what we just plotted. Okay, and we'll try to compare this curve against what we had. Okay, so this was the original curve that we had from W by L as 1.5, but W is 1.8 micron and L equal to 1.2 micron device. Everything was same except that the length, the technology node was 0.25 micron and W was 0.375. So we had these two curves, these two curves generated, but you see there is a difference between this curve and this curve. Okay, so let me try to bring up the exact differences, the exact observations, and try to explain the concepts, what happens when we go to a lower node. So let's try to do all this in the next video. Thank you.